Hello everyone. In this video, we are going to discuss the derivation of the security market line or the SML. In class and in a previous video also, we have seen the equation for the capital market line already, which is this equation here. I have pre-written that for you. And we have also noted from that equation that this item here, the reward to volatility ratio, is the slope of the CML, which basically tells us the change in the expected return of the portfolio as a result of the change in the risk of the portfolio as measured by the standard deviation. Let us now proceed forward towards the security market line. One of the assumptions in the capital asset pricing model is that all investors have identical expectations. So since they have homogeneous beliefs about expected return and risk, let us say that they all prefer to hold the market portfolio, which we are going to give a name M, and this is our risky portfolio, the market portfolio M. This means that for such investors who are having common beliefs, who share the same belief, their expected return, let's write that as R bar, would simply be equal to the expected return from the market, and the risk from their investment, the standard deviation that is, would be simply the standard deviation of the market returns. Now, if we wish to introduce a new asset, it must be evaluated in terms of any additional return and risk that it brings with it. Let us give a name to this new asset. Let us call this asset I. Now this would mean once we have asset I into the picture, we are going to have a portfolio with us which we will call P, and this portfolio P would be partially invested in the market and the other part would be invested in this asset I. So that if we want to write the expected return from portfolio P, we are going to have to write the proportion that we allocate to this asset I, let's call that W, multiplied by the expected return on this new asset I, plus we are going to have only 1 minus W proportion of money left to invest in the market portfolio, and that would be multiplied by the expected return from the market. If we simplify this, we are going to get W times RI bar minus RM plus Rm. We have worked with a similar equation when we were deriving the CML equation. If we want to write the risk of this portfolio, the standard deviation of the portfolio would be simply the square root of the variance. Well, what would be the variance then? W squared, which is the weight that we place on the asset I, multiplied by the variance of I, plus the weight that we place on the market portfolio M squared times the variance of the market, plus 2 times W times 1 minus W times the covariance between this new asset I and our market portfolio M. And because we are writing the standard deviation, we take a square root. We could simplify this, and we have done that in a previous video also. What we did was we opened up this square here, 1 minus W whole squared, so that would give us 1 squared plus W squared minus 2 times W, and all of that would be then multiplied with this variance of the market, and we would also multiply out these terms. When we do that, this is what we would get: W squared times variance of our new asset I plus variance of M plus W squared times variance of M minus 2 times W times variance of M plus 2 times W times covariance between I and M minus 2 times W squared times covariance between I and M and raised to the power of half. We have just simplified this expression here. Now let us notice a couple of things. If we were to return to the original position, which was that our entire money was invested in the market portfolio, then W would become 0, isn't it? We would not be investing anything in the new asset I then. In that case, what would be our expected return on the portfolio? Well, this W would become 0, so therefore this entire term would become 0. That would mean that the expected return on the portfolio would be only RM. I should have written a bar here, expected return on the market. So that would be our expected return, which would be the same thing as this. We would return to the original position. What would happen to the risk? Well, let's see. This is our standard deviation. So we have a W here. If we write a 0 here, this item becomes 0. We have a W here, so this also will become 0. This also has a W, so this is also 0. Likewise, this will be 0 and this will be 0 as well. So what you are going to have inside the bracket is variance of the market raised to the power of half, which would be nothing but standard deviation of M, which was our original position here. The question that we are interested in answering now is that what is going to be the change in the expected portfolio return by introducing this new asset I. So we can write the change as the partial derivative of the expected return of the portfolio with respect to W. Well, this is our return of the portfolio. If we take a partial derivative with respect to W, all that we are going to have is Ri bar minus Rm bar. We can also do the same thing for the risk item. What is going to be the change in the standard deviation of the portfolio? So we can take the partial derivative of the standard deviation of the portfolio with respect to W. And we had done this before in a previous video, so I'm going to leave that to you as practice. I'm just going to give you the final result here. You should do it yourself and check that you get this. W times variance of I plus covariance between I and M times 1 minus 2W plus variance of M times W minus 1, and all of this divided by the standard deviation of the market return. Alright, so let us evaluate our position from the original position where W was equal to 0. If W is equal to 0, then this item is going to remain unchanged. We are simply going to have Ri bar minus Rm bar. There is no W item here, so this remains unchanged. What happens to this item here? The change in risk. Well, we have a W here. If we use a 0 value for W, this whole thing is 0. If we write a 0 here for this W, what we are going to have is 1 minus 2 times 0 is going to give us 1 minus 0, which will be 1, and 1 multiplied by covariance between I and M is going to give us simply covariance between I and M. What happens in this term? If we write a 0 here, we are going to have in the bracket 0 minus 1. So minus 1 times variance of the market is going to give us variance of the market, negative. And we are going to divide all this by the standard deviation of the market. Alright, now let us see what we can do. We also want to answer another question, and that is how much did the expected portfolio return change in response to a change in the portfolio risk? So basically we are wanting to write this expression, the change in the expected portfolio return in response to a change in the risk of the portfolio, which is going to be equal to this item here divided by this item. Because if I write here change in expected portfolio return over change in the weight divided by a change in the standard deviation of the portfolio divided by the change in W. This item is going to go away with this, leaving me with this divided by this, which is what I wanted. So this is going to be equal to, well, this is equal to Ri bar minus Rm bar, and this item is equal to this item here, which is covariance between I and M minus variance of M divided by the standard deviation of M. Now let me scroll up to verify that this item here is also the slope of our CML that we had seen before. Let us see that. This item here is the slope of the CML, which we have defined as equal to this, which means that this item here that we have written must be equal to the slope of the CML. So we can equate the two. So we can write here Ri bar minus Rm bar divided by covariance between I and M minus variance of M divided by the standard deviation of M is actually the slope of the CML, which is Rm bar minus Rf, all divided by the standard deviation of M. From this equality we can make Ri bar our subject of calculation, and we can solve this for Ri by doing some algebraic manipulations. Let us try to do it. Well, the first thing that I'm going to do is to take this standard deviation of M upstairs here, so that I can write this as Ri bar minus Rm bar multiplied by the standard deviation of M, all divided by covariance between I and M minus variance of M, and this is equal to Rm bar minus Rf over standard deviation of M. So what I'm going to do now is to look at this item and take it over to the other side. When that happens, this is going to go into the denominator, and this thing is going to become variance of the market. So let me make that change. So let me just take this item from here, let me erase this from here, and make this equal to variance of M. Now what I'm going to do is to take this item across, where it's going to get multiplied with this item. So let us write it afresh. Ri bar minus Rm bar is going to be equal to Rm bar minus Rf multiplied with covariance between I and M minus variance of M, all divided by variance of M. Now let us see what else we can do. We can take this minus Rm bar also over to the other side, so that we can write Ri bar is equal to this whole item here. So let me write that out again. Rm bar minus Rf times covariance between I and M minus variance of M, all divided by variance of M, and plus we are going to have Rm bar. Now let us simplify this. We are multiplying out these brackets, so we are going to have Rm bar times covariance between I and M minus Rm bar times variance of m minus Rf times covariance between I and m plus Rf times variance of m. I also want to do one more little thing. I want to have this variance of m as the common denominator for the entire thing. So what I'm going to have to do is to multiply this with this and write here plus Rm bar times variance of m, and then I can have variance of m as the common denominator for everything. Now let us see what we have. We have this minus Rm bar times variance of m, and we have this plus Rm bar times variance of m. So these two are going to cancel out. From the remaining terms, let us try if we can collect some terms. Let us collect covariance between I and m. So inside the bracket, I'm going to have an Rm bar from here, and from this item here, I'm going to have an Rf. So we have dealt with this term here, we have dealt with this term here, this one has cancelled out with this. What else remains? We have this term left here, so let's write that Rf times variance of m, and all divided by variance of m. Let us separate these terms now and see what we get. We have Ri bar is equal to, I can write this part separately, and then I can write this part separately again. So let us write down the first part. We are going to have covariance between I and m over variance of m multiplied by Rm bar minus Rf, plus we are going to have Rf times variance of m divided by variance of m. So this is going to cancel with this. So what we have now, Ri bar will be equal to, I'm writing this item first, Rf plus, now this item, covariance between I and m over variance of m times Rm bar minus Rf. We know from a previous video that this is nothing but equal to beta of I, so we can make that change and write Ri bar as being equal to Rf plus beta of I times Rm bar minus Rf. This is our SML equation that we see in the textbooks. And we can also write an alternative form of this equation. We can write the excess return on the asset I, which I'm writing by just transposing this Rf to the other side, would be equal to beta of I times the excess market return, which is this. So this also is equivalent to the previous equation. Well, in another video, we are going to take some data and test the CAPM model. Basically, we are going to be testing this equation here, this one, that excess returns on a security or an asset is simply equal to beta I times the excess return on the market. And the way we can do this is by drawing a parallel with the normal simple linear regression. So let's assume this to be equal to y, which would be equal to a plus b, which is the slope of the regression line, times the independent variable x. So let us map out the terms. This Ri bar minus Rf corresponds to this y. But in this equation, we don't have any intercept, which means that a, or the intercept, will have to be 0. And then this item maps to this b here, and this rm minus rf maps to this x here. So when we are running the regression and testing the CAPM, we are hoping that we are going to get an intercept which is equal to 0. In other words, if we wrote our single index model, this would be actually our alpha. So we are hoping that if CAPM holds, alpha of the security would be equal to 0. We are going to see that in another video. For now, it's bye bye. See you later.